My pleasure to introduce Dr. Marika Holland, who's a senior scientist and at the, I guess at NCAR, right? Let me just make sure. Yeah. So Marika has done a lot of work, is very well known for her work on looking at the impacts of climate change in Arctic, on the Arctic climate, in particular, looking at sea ice and sea ice climate interactions. And so I think with that brief introduction, and I apologize for not doing anything more, I'll let Marika introduce herself further and introduce her presentation today.
Yeah, thanks, Tristan. And it's really nice to have the opportunity to chat with you all today about some of my work. So I'm going to share my screen. Okay, and I'll put it into presenter view. And hopefully you can see that and you aren't seeing my notes. You're just seeing the slide view. Does that look good?
Yep, that is correct. Yep.
Great. Thank you. Yeah. So I'm Marika Holland. I'm a scientist at NCAR. And as Tristan mentioned, I primarily look at polar climate. And in today's talk, I'm going to be talking about some aspects of predicting Arctic sea ice. And I'm going to look at both seasonal timescales. That's actually going to be the last part of my talk. And also multi-decadal timescales. And I'm going to talk a little bit about how these two things interact, and in particular, how multi-decadal changes in sea ice cover influence the seasonal predictability characteristics of the ice. So actually, a lot of people have collaborated with me on this work. I don't have their names listed here, but you will see their names as I go through the talk when I reference different papers. And in particular, Steve Vavris, and I saw Steve's face before we went into the slideshow. So I know Steve's on the line. He's actually contributed to some of this work, and you'll see that as we move through the talk. Okay, so on to, let's see. Yeah, okay, so first I'm gonna give, in terms of an outline for my talk, I'm gonna give a little bit of background on sea ice processes and the kind of sea ice processes and feedbacks that I'm thinking about when looking at these questions. Then I'll talk a bit about predicting sea ice on multi-decadal timescales, then seasonal predictability of sea ice, and I'll end with some final thoughts. And feel free to ask questions along the way or put things in the chat for discussion later as we go through this. Okay, so on to the background. So I think whenever you talk about Arctic climate change, it's useful to point out that the Arctic is changing very much on a system-wide scale. And I think it's actually not too strong a statement to say that the Arctic as we know it is really disappearing. We're seeing changes occurring across the entire Arctic system. So in this talk, I'm primarily going to talk about sea ice and sea ice loss. And here you can see September ice concentration trends from 1979 to 2017. The gray area here is just where there's an outage from the satellite data. You can see that there's extensive sea ice loss along the perimeter of the Arctic ice pack that has been observed since 1979. There's also dramatic changes happening over Greenland, and this shows the Greenland melt trend from 1958 to 2017. Of course, that meltwater is entering the ocean, causing changes in sea level, causing changes in ocean salinity and circulation. This is all happening in the context of a very rapid and large-scale Arctic warming. So this shows the changes in 2020 relative to 1981 to 2010. 2020 was the second warmest year on record in the Arctic. That Arctic warming is happening at about twice the rate of the global average. So this very large warming occurring. We're seeing changes occurring on the landscape as well, increases in wildfires in the Arctic. Those, of course, are emitting aerosols and carbon into the atmosphere, which are also causing further changes in the climate system. And we're seeing changes in terms of the coastal system. So rapid coastal erosion occurring as a consequence of sea ice loss, warming, increased wave action on the coastline, and the thawing of these ice-rich permafrost bluffs. So this is just some of the changes happening in the Arctic. There are many more. There's vegetation changes, there's hydrologic changes, and all of this is part of this large-scale Arctic change that's underway, happening very rapidly and affecting really all aspects of the Arctic system. So in this talk, I'm going to primarily focus on Arctic sea ice, however. So this shows the changes in Arctic sea ice over the satellite era. So this is September, the September time series from 1979 to 2020. You can see again this downward trend in the sea ice. The blue line is just a linear fit to that data. We've lost something like 40% of the sea ice relative to the kind of 1980 conditions over this record. So the question I'm asking is really what happens next? So where do we expect things to go on multi-decadal timescales or on seasonal timescales? And when thinking about this question, it's important to consider what sea ice processes might be at play and how they might affect things. So I'm just going to have a couple slides here to emphasize the fact that sea ice processes are climate state dependent. And that, of course, affects feedbacks in the system. It influences the predictability of the system, et cetera. So one of these sea ice processes that's climate state dependent is sea ice growth. So here you can see a schematic of sea ice, snow covered, on top of the Arctic Ocean, say, with cracks, leads in the sea ice cover. The ice growth, which happens at the base of the ice in the Arctic, is primarily driven by the conduction of heat through the ice. And so it's related to the temperature gradient through the ice system, and that's related to the ice thickness primarily. So what this means is that thinner ice will grow more rapidly because you've lost the insulating effect of the ice cover. And this relationship is nonlinear with thickness. It's actually 1 over the thickness. So what this means is that you have an ice growth relationship that you can see on the lower right panel, where as a function of ice thickness, ice growth increases in the thin end of a thickness distribution, say. What this does is it means that there's a negative feedback on ice thickness. So as ice thins, it basically wants to grow more because of the this ice thickness, ice growth relationship. And that means that it kind of resists that thinning of the ice. So it actually is kind of it's a negative feedback on the system. So that'll be important as I talk through sort of predictability aspects of sea ice. There are feedbacks in the system that are positive, of course, and the most well-known of these is the surface albedo feedback. And that also is ice thickness dependent. So it changes with the climate state. So as ice thins, melting is more efficient at opening up water. And that makes a lot of sense. It's much easier to completely melt away a thin ice cover than a thick ice cover. It requires less heat. And that relationship is also nonlinear with ice thickness. So this lower right panel shows the change in open water formation per centimeter of ice melt as a function of ice thickness the previous spring. And so what you see here is that, as you move into a thinner ice regime, you actually get more open water formation for the same amount of ice melt. And so this has implications for the surface albedo feedback as you replace ice with open water, and that causes a dramatic change in the surface albedo. So this is another aspect of sea ice that is climate state dependent. Okay, so that's just a little bit of background in terms of kind of the processes that I'm thinking about when I think of sea ice in a changing Arctic climate, and some of the processes that might come into play. So now I'm going to turn to predicting sea ice on multi-decadal timescales. And just to back up in terms of predictability itself, there are two different aspects of predictability. Often they're referred to as predictability of the first kind and predictability of the second kind. For this part of the talk, I'm going to be talking about predictability of the second kind. I'll return to the other type of predictability at the end of the talk. But basically, if you look at this schematic on the right, so this is, say, sea ice or any sort of climate variable, say, as a function of time. And predictability of the second kind is basically trying to predict a change in the system subject to some external forcing change. And so in this case, the biggest external forcing change we're dealing with is the rise in greenhouse gases in the atmosphere. So this can cause a predictable change in the sea ice cover, say, a reduction in sea ice over time, for example, as indicated by this kind of orange-red shading. But we're not trying to predict the conditions at a particular year. We're trying to predict the statistical properties of climate and how those statistical properties change. So not just the mean state of the system, say, but also its variability and other aspects. So this first topic I'm going to discuss in terms of sea ice loss and sea ice on multi-decadal timescales is really this predictability of the second kind. It's looking at the prediction of the statistical properties of the climate subject to some external forcing. In this case, they're all projections from a climate model into the future where there's rising greenhouse gas concentrations in the atmosphere. And that's primarily where our predictable signal is coming from. But in looking at that predictable signal, we also want to look at the noise around it. So the internal climate variability, that can kind of mask a predictable signal in the sea ice. There also can be predictable changes in the internal variability itself. So I'm going to quantify these things using coupled climate models. And I'm going to quantify internal variability and force change by looking at a large number of climate simulations. So this shows a schematic of a climate model. I'm talking about, a comprehensive Earth system model, atmosphere, oceans, sea ice, land, coupled system model. And in particular, I'm going to be looking at results from the community Earth system model. So the change over time is going to be a combination, of course, of internal variability that just arises from the internal dynamics of the system, and then a forced response, which is going to be driven by changes that we apply in the model to external forcing, things like greenhouse gas concentrations in the atmosphere. So I'm going to look at the forced response in my system by looking at a mean of many different ensemble members. I'm going to look at internal variability by looking at the variations around that ensemble mean. So basically, in order to do this, I'm using a large ensemble. This is a large ensemble from the community Earth system model. It's often referred to as the LENS. This set of simulations, there's 40 individual ensemble members. All of those ensemble members are run with exactly the same model, exactly the same forcing. So same greenhouse gas concentration changes, same ozone changes in the atmosphere, same emissions of aerosols, same solar variability at the top of the atmosphere. So they all have exactly the same forcing. They all have exactly the same model. They only differ very slightly in their initial condition in 1920, but they have a round-off level change in the air temperature. But because the system is chaotic, those simulations will then diverge over time. And by looking across our ensemble members, we get a measure of internal variability. By averaging all those ensemble members together, we get a measure of the forced response because we average out that internal variability noise, and we're left with this common aspect of this identical forcing. So that's how I'm going to quantify things in this next part of the talk. And just to show you that the model does a good job of simulating Arctic sea ice conditions. I just have several different metrics here. The Northern Hemisphere ice extent in the model compared to observations, the ice thickness in the model, which I don't have an observational comparison, but it looks quite similar to what you expect from observations, with the thickest ice here along Greenland and the Canadian Arctic archipelago, and thinning as you move across the Arctic. The September Northern Hemisphere ice extent on the lower left here, relative to observations in red. And you can see the range across our 40 ensemble members in the blue here, the ensemble mean in the black, and the observed record in red, which is on the lower end of our ensemble, but within the ensemble spread primarily. And then this just shows 35-year trends as simulated across our 40 ensemble members for the 1979 to 2014 time period in the blue histogram here relative to observations. So again, observations lie at sort of the lower end of what our model simulates, but within the trends simulated across the different ensemble members. And again, those different ensemble members only differ in their kind of sequence of events associated with internal variability, the chaotic aspect of the climate system, which on these multi-decadal timescales is not predictable. Okay, so that's just to kind of give you a flavor that the model does a lot of things right in terms of its Arctic sea ice simulation. So in terms of projections of sea ice, so I'm showing here again that September ice extent time series on the left, and also the Arctic ice thickness time series in January on the right. And you can see that in both cases, things are relatively stable. There's a lot of variability, which is indicated by that blue shading. So an individual ensemble member might vary from one year to the next, say, but overall, they're quite stable up until the latter part of the 20th century, at which you start to see reductions in sea ice extent and thinning of the ice pack overall. And these simulations reach near ice-free conditions around the middle part of the 21st century. So what are the thickness mass budget changes that support those changes in the sea ice and affect those changes in the sea ice state? So I'm going to show some figures of the changing mass budgets in the Arctic. And just to familiarize you with what I'm showing, this shows the climatological ice mass budget in the model at the end of the 20th century. And I'm averaging this over an Arctic domain, which is identified by these gates. So really, I'm not looking at the northern North Atlantic or the northern North Pacific. I'm really looking at the Arctic basin itself. And so you have melt and growth, which is going to cause ice to grow in the fall and winter months, and then melt, causing ice to decline in the summer months. So you can see that in the black bars here on the right. And then there's also a small amount of ice transport out of this domain, primarily because ice is actually transported out of the Arctic into the northern North Atlantic. So that's this divergence term here in red. So that's the climatological budget. And this shows the changes in the sea ice mass budget over time in our 21st century simulations. This is an ensemble mean change. So this is the forced change in the system, due primarily again to rising greenhouse gases. The white or black line here is the mean, the net mass budget change. And you can see it's always negative. So we're thinning the ice, we're losing ice volume in the Arctic. But it's made up of these counteracting changes in melt and growth. So you have increased melt, which is a larger loss of sea ice over time. But you also have increased growth, meaning that in the winter months, the ice is actually growing more than it was in the late 20th century. You also have less ice being transported out of the Arctic. So this is a positive anomaly in the ice mass budget. And that's because the ice that's being transported out of the Arctic is thinner, primarily. But this increased growth is interesting. So it's associated, again, with the fact that thinner ice grows more rapidly because you've lost that insulating capacity of the ice. So that winter sea ice growth is counteracting these changes in the sea ice state, and it's keeping the sea ice more stable. It also, again, has a thickness dependence. So these ice growth increases are particularly true in areas of thin ice. And that means that the distribution of ice within the Arctic changes as well. So this shows a histogram of the ice thickness in April in the 1980 climate in red and the 2020 climate in black. And you can see here that it's not just that we're shifting the distribution to thinner ice cover, we're actually changing its character quite dramatically. So basically, with the thinning ice, you're losing this thick end of the distribution, the thick multi-year, several year ice, and you're replacing it with first and second tier ice. And that ice is much more stable. And it's more stable because it again kind of counteracts changes in its thickness because of this negative ice thickness, ice growth rate feedback. So that has implications for other changes in the system. So I'm just bringing you back to this September ice extent time series, because now we're actually going to look at the anomalies around that ensemble mean change. So not just, so basically, how is the internal variability changing in the system? So I'm going to remove and subtract out the ensemble mean change, which is shown here by the black line. And what we're left with is the anomaly around that. So this shows the internal variability. I'm actually showing there's 40 individual black lines here. So each of my ensemble members is shown here. And just visually, you can see that, this internal variability plus or minus 1 million square kilometers, say, those are the kinds of anomalies that we get in the 20th century. But as you move into the 21st century, that variability grows until you hit basically ice-free conditions in the Arctic, and there's basically no sea ice left and no variability left in the September sea ice cover. So you can see by eye that, this grows. We can quantify that by just looking at the standard deviation across those 40 ensemble members. So how variable is it across those 40 ensemble members? And that's what's shown here on the right. And you can see what you see here by visual inspection, that, that variability grows in the early part of the 21st century. This is true in September. It's also true in other months if you look later into the 21st century. And there's a number of papers that have looked at this behavior, and you can see some references here. So why is it that we get this increase in variability in the sea ice in a warming climate? Well, some of it is associated with this change in the distribution that I mentioned earlier. That's a consequence of the changing sea ice mass budgets. So this again shows that histogram of ice thickness in the 1980 climate in red, the 2020 climate in black, showing that you've shifted and lost this thick multi-year ice, replacing it with thinner first and second tier ice. And that ice in that kind of 1.5 to 2.5 meter thick range in terms of its springtime ice thickness is the ice that's really vulnerable to meltdown. So this shows the bottom histogram here shows the April ice thickness that is present in regions that have highly variable meltout the following summer. And what you can see is that in both the 1980 climate and the 2020 climate, most of that ice resides in this sort of 1.5 to 2.5 meter thick range. So that's ice that can either melt out thermodynamically or by ice transport is thin enough that you can actually expose the open water in those regions the following summer. And that's also the region of the ice pack that we're thinning into in terms of the changes in the ice thickness distribution. So some of these changes in the summer ice area variability are increasing because ice thins into this domain where there's highly variable meltout, where with a particularly warm summer, for example, you might melt out that ice, but a particularly cold summer will retain that ice. So that's part of the reason why we get this increase in the internal variability in the ice extent with a warming climate.
Marika, could I ask a question at that point?
Yeah.
Yeah, thank you. What about ice volume? Is the ice volume substantially less variable, or does it vary nearly as much?
So the ice volume or ice thickness, which is, the integrated ice volume. Ice volume is the integrated ice thickness. Its variability actually declines over time. It's more variable in the 20th century, and it decreases in the 21st century because this negative ice thickness, ice growth rate feedback is stronger for thin ice. So it actually causes thickness anomalies or volume anomalies to decline over time, which is different than the ice area or ice extent variability.
Okay,
so
thanks.
yeah, it's interesting dynamics in how the sea ice works.
Yeah, thank you.
Sure. So how do these different factors, we have, a changing distribution of ice thickness, we have changing internal variability in the sea ice, we have increased open water formation efficiency that allows more ice to melt back in the summer because the ice is just thinner. How do those things all interact to affect the transient sea ice response in the future? So it's kind of illustrative to look through individual ensemble numbers to answer this question. So here you see observations, and then in the black, I'm going to just show a series of just pulling out different ensemble members, just to give you an idea of how variable the sea ice really is in our projections of change. So in this case, the model and the observed trends are quite similar. And, then the sea ice has this very high variability moving into the future and reaches near ice-free conditions at the middle of part of the 21st century. We have other ensemble members. Again, the only difference between these is internal variability, this chaotic aspect of the climate system, which have much less sea ice loss compared to the observations. Others which have really very little sea ice loss up until 2020 or so, and then a dramatic decline in just about 30 years, where most of the ice pack is lost. Some of our ensemble members show increases in sea ice, even in the 21st century, on decadal timescales, when internal variability counteracts the anthropogenic force change. So we have all these different flavors of what might happen in the future, including increases in sea ice, followed by abrupt, rapid ice loss events. And all of those things are plausible futures. They only vary in terms of this internal variability. That internal variability is chaotic. We can't predict it on multi-decadal timescales, but we can say some things. What we can say is that all of these ensemble members go ice-free at the middle part of the 21st century. By 2080, the ice in September is gone in all of these ensemble members. So there's this strong boundary forced detectable change in terms of the long-term sea ice loss. On multi-decadal timescales, they're all losing ice. They all have this large and growing internal variability. They have possibility of increases in sea ice on decadal timescales, rapid declines on decadal timescales. And we can quantify some of these things. So in particular, can we quantify when a forced signal emerges from that really large internal variability noise in the system? So we've done that here. This shows time series, and now I'm actually showing it for a number of different large ensembles from 5 different climate models. So each of these colored lines is a different climate model. And then the observations is shown in gray. The model results go from this kind of transparent to solid coloring when we can detect in those model simulations a forced signal. And we do that by looking at when the decadal mean change in the sea ice extent is greater than the decadal variability that we have from a reference period. And we do something simple here. It's just twice the standard deviation of that decadal variability from a reference period. So interesting, even though there's this very large internal variability, we can detect a forced change around the 1990s. And I think what was particularly surprising to us when we did this work was that that detectable change is very similar across all of these ensembles. So it basically occurs in the mid-1990s across all of these different large ensembles. And all of these different climate models have very different biases in their sea ice cover, in their mean state, but they all simulate this forced signal emerging around the mid-1990s. So we do think that there's a forced signal in the sea ice loss. But the internal variability and the fact that that's growing also has challenges for us. And one of those challenges is in using the observed record to try and constrain future sea ice loss. So this shows some work from Dirk Knotts and Julian Struve from a few years ago, where they looked at the sea ice area in observations. This is shown in the blue symbols here, relative to the CO2 emissions. And it's a fairly linear relationship here. So they argued that perhaps we could use that to extrapolate into the future what CO2 concentrations or CO2 emissions would give us ice-free conditions in the Arctic. So we can do that same sort of analysis using these large ensemble simulations, where again, the simulations only differ in terms of their internal variability. So here we're looking at basically from our CESM1 Large Ensemble, the slope of this line in the model across the 40 ensemble members. And then I'm just showing a histogram of that. So this is the ice area change per CO2 change. So again, slope of a linear fit. And you can see it differs quite dramatically across our ensemble members, because there's a lot of internal variability, even acting on these multi-decadal timescales. So if we take those and then extrapolate out into the future and look at when they would reach a near ice-free condition of 1 million square kilometers of sea ice in the September Arctic, you see that, again, they range, the range is very large. It's larger than what the climate model simulations actually simulate, which is shown in black. And it's also shifted to higher CO2 levels. So this suggests that the internal variability, if you trust the internal variability from these climate models, is just so large that it raises this challenge of using the observed record to constrain where we're going to head in the next several decades. This is true for CESM. It's also true for other climate models, and I'm showing basically the same analysis, but now performed on one of the GFDL large ensembles, where you can see that in this case, doing this extrapolation from a linear fit over the observed period record actually gives us an under simulation of what the model actually simulates in terms of CO2 levels for a sea ice loss. So there's nuances here that bear further analysis and further work to try and understand, what the real limitations are in using the observed record to look at future sea ice loss. And again, that's all within the context of coupled climate models and the coupled climate model variability that we simulate. And I just want to emphasize that there's evidence from the observed record that there's also large internal variability. So this shows, again, that time series of September sea ice extent. And, the linear fit here in the blue dashed line over the entire record. But you can also look at linear fits over different periods of this. And in particular, the last, 10 years or so has shown very low sea ice loss. So we do have these large kind of multi-decadal changes in ice trends over time. And I'll just note that numerous studies have suggested that internal variability may have reinforced this ice loss by perhaps 50%. So internal variability, there's evidence that that's playing a role in the observed ice loss as well. So I'm going to skip this next slide because I realized I'm going too slow and I'm not going to get to the last part of my talk, which is looking at seasonal predictability of sea ice. But just to note that we are looking at other months besides September as well, although a lot of focus is on September sea ice loss. Okay, so now I'm going to turn to some work we're doing on seasonal predictability of sea ice. And in particular, we're interested in how the changing climate and the changing sea ice state affects the predictability characteristics of sea ice on seasonal timescales. And a lot of motivation for wanting to look at sea ice predictability on seasonal timescales comes from that really large internal variability. So this shows a histogram of sea ice conditions in September, the sea ice extent in our large ensemble. The blue here is for a pre-industrial climate state. So there is variability around that, around a mean state. It's actually quite considerable. But these pre-industrial climate states are also very steady. They're stable on sort of multi-decadal timescales. What's shown in red is the distribution of sea ice extent for this 2010 to 2019 time period from our CESM Large Ensemble. And so you can see that the spread here is enormous. So you can have, in the same decade, a sea ice cover that looks like this. So the upper panel is one of these low members here. Ice extent, that's just a few million square kilometers, say. And this actually occurred in 2017 in a particular ensemble member. You can also have, a situation like this, where most of the Arctic basin is actually ice covered. It's at the higher end of this distribution. This particular one occurred in 2013 in a different ensemble member. And again, the differences here are primarily associated just with internal variability, different weather systems in the summer Arctic, et cetera, that drove different sea ice changes. So, of course, we would like to be able to predict these changes or these conditions in the sea ice on a seasonal timescale. So say predictions started now to predict what might happen next summer, because this has a lot of implications for marine access in the region. So there's a lot of stakeholders that are interested in these predictions on seasonal timescales. So now to return to this kind of predictability science. So in this case, we're really looking at predictability of the first kind. And this is predictability that arises from a knowledge of the initial state of the system and the fact that those initial conditions, there's some memory associated with them, and they can give us some predictive capability. So this is really an initial value problem. Of course, because the system's chaotic, there's a sensitive dependence on those initial conditions that limits predictability. And it's also, the time scale depends on the system. So, for weather, those predictions might be good for a couple weeks. For ocean conditions, it might be predictable for several years, perhaps out to a decade. And so we're looking at this topic for sea ice, and in particular, sea ice predictions that are kind of months out to a year or so. So it's really looking at this kind of blue, purple shading here, where we know the initial state, we're trying to predict into the future. And of course, when that spread across ensemble members, say, reaches what you expect from internal variability, your predictive capability is lost. And we're particularly asking this question of whether our predictability characteristics on seasonal timescales change with the changing climate state. So in order to assess this, we've performed experiments that often are referred to as perfect model predictions. And they're perfect model predictions, not because the model is perfect, but because we're using the model to predict itself, essentially. We also have a near perfect knowledge of the initial conditions. So it's basically this framework to assess the inherent predictability characteristics in the system. So what we've done is we've taken initial conditions from our large ensemble, so the simulations I've been discussing all through the talk, and we know those initial conditions exactly, perfectly. And then we add a small error in the initial air temperature, just a round off level change in the air temperature. And just that very small error means that over time, these simulations will diverge because the system is chaotic. So we've performed these initialized predictions for each decade from 1980 to 2030. We actually do 4 different sets for each of those decades. You can see an example of this on the left. And we've done that because we want to kind of sample within the internal variability of the system, so what kind of 1980 type conditions can we get? So we've done 4 samples for each decade. And then we run just for a year predictions. And so you can see here on the left, an example of this. And so in this case, I'm showing the Arctic ice volume from those predictions. Again, there are these 4 different sets indicated by the 4 different colored lines. The dashed line here is the range across our large ensemble. So that's a metric of the internal variability in the system. You can see all of these actually have identical ice volume at January 1st when they're initialized. But you can see over time that those ice volume starts to spread, and that's because the errors in our initial air temperature kind of start to spread and contaminate the entire system, essentially. And you can see that that spread particularly increases in the summer as we thin the ice. And so at a certain point, your predictability declines. We can quantify this by looking at the variance across our ensemble members. And so this shows the gray lines here is that variance in the ice volumes, again, for this example. The blue is basically an average of that for all those different ensemble sets for this. In this case, it's the 1980 predictions. And then the internal variability is shown in red. So basically, if we're statistically lower than this internal variability, then it means that the initial conditions are giving us some predictability in our system. And it's better to actually predict from do an initial value prediction than just say pull from a climatology. And you can see in this case that ice volume, the variance in our prediction ensembles is less, which means that we have predictability in ice volume in this 1980 climate state for at least a year, and likely for years into the future, given that how different these variance estimates are. So that's for ice thickness or ice volume. What about ice area? So this shows the same metric, but now I'm looking at ice area. So these again are same predictions that were initialized on January 1st, and I'm just looking at the summer months here. You can see that the internal variability or the variance, the spread across our ensemble members grows. The internal variability also grows in the summer. There's more variable sea ice area in the Arctic Ocean in the summer. What's interesting is that while ice volume was predictable for the first year, the fact that these 2 lines lie on top of each other suggests that there's really no predictability in ice area for these forecasts that are initialized on January 1st. So for this 1980 ensemble set, there's really no predictability in the sea ice cover the next summer. But if we look at these future decades, in 1990, not future from now, but future from 1980, 1990, 2000, 2010, 2020, 2030, now you see that our prediction ensembles in blue are distinctly lower and different than the internal variability, which is in the red line. So this suggests for these later decades, initialized predictions do give you predictability for summer sea ice conditions, even from a January 1st initialization. So, 9 months out, 8, 9 months out, you have predictability in the sea ice. We can look at that spatially as well, and that just confirms what you saw in those hemispheric metrics. So this shows a metric of the predictability and September ice concentration across these different decades. So this is for September. Blue colors, dark colors are regions where it's more predictable. So this is just a particular kind of skill metric. And it's also true if we only consider regions of the ice pack that are now kind of highlighted between these lines, where there's high ice area variability. So, in the 1980 climate, we're not terribly concerned about predicting sea ice in this interior region where it's almost always ice covered. We're really interested in the areas where there's highly variable ice area. And you can see in that case too, that the predictability characteristics change. And in particular, this 2010 time period seems to have the highest predictability. That's true if we look at aerial kind of average metrics, or we look at things spatially. Okay, so why do we get this change in the predictability in the different decades? So previous work has shown that ice thickness is one of the really important predictors of summer ice area. And that's because ice thickness anomalies are long-lived, they last a long time. And those ice thickness anomalies can also affect how much summer meltout there is, how much ice area loss occurs the following summer. So we can think about the loss of predictability as being related to those two things. So first, the growth of ice thickness errors from that initialized state where there's no error. And so this just shows for one of those ensemble sets how those ice thickness errors grow over time as indicated by the spread across our ensemble members. So we can quantify that by looking at the spread across these initialized ensemble members. And then the second aspect of this loss of predictability is how those ice thickness anomalies at the beginning of the melt season affect the meltout of sea ice and affect how much open water is formed over the summer. So we can quantify that by looking at that relationship of ice volume anomalies in July relative to ice area anomalies the next September. And you can see there's a relationship here. The symbols are different individual years. And we can just do a regression of those two things to quantify this. So we can do that across our different ensemble, our different initialized ensembles for the different decades. And so this shows the growth of ice thickness anomalies from their initialized state, that first aspect of a loss of predictability. And you can see that those differ. And in particular, they're smaller in the warmer climate. And that's because of this ice thickness, ice growth rate relationship and the fact that anomalies in thin ice are more strongly damped, meaning that their error growth is smaller. So it's related again to this ice thickness, ice growth rate relationship. But we find that the meltout sensitivity, so basically how those ice thickness anomalies affect meltout the next summer, grows in the warmer climate. And that's related to the fact that it's easier to melt out thin ice. So if you have ice in that kind of 1.5 to 2.5 meter thickness domain, you might melt it out, you might not. It depends on the summer conditions. And so those ice thickness anomalies at the beginning of the summer meltout season have a larger impact on how much sea ice loss you get over the summer as you move into this warmer climate. So this just is showing that relationship as a function of time. So we have these two competing aspects on the loss of predictability: the growth of ice thickness anomalies from the initialized state, which are smaller in a warmer climate, and how those ice thickness anomalies affect summer meltout, which are larger in a warmer climate. So what this means is that we sort of have this sweet spot for predictability where there's a modest growth of these errors in ice thickness over time. And there's also a modest influence of those ice thickness errors on meltout the next summer. And so those two things combine to give us higher predictability in this sort of early 21st century climate when we're looking at these seasonal timescale predictability characteristics. Okay, so some final thoughts. So sea ice processes, related feedbacks, and internal variability are all climate state dependent. And the thickness of sea ice and the distribution of that thickness of sea ice within the Arctic is particularly important for these things. This affects multi-decadal sea ice loss with aspects such as growing ice area variability, difficulties in using the observed record to constrain future sea ice loss, etc. It also affects these seasonal predictability characteristics of sea ice in the warming climate. And it also has implications for trying to understand differences across models. And this was nicely pointed out in a recent paper by Francois Massenet and co-authors, that models have different mean state biases. And that means that these aspects of decadal scale changes, predictability characteristics, internal variability, and the magnitude of ice area anomalies, say, are all going to differ because those models have different mean state biases in their climatology in the late 20th century, say. And this suggests that simulating a good present day sea ice state is really important if we're to have reliable predictions. And so that's something that we should be striving for in our climate models, is to improve the mean sea ice state as simulated in those models. So with that, I'm happy to take any questions if there are some, and thanks so much for your attention and listening.
All right, thank you very much for the stimulating talk. There is one question already in the chat that came from Grant. Maybe Grant, do you want to go ahead and ask your question?
Sure, I'll go ahead. Thanks. I enjoyed the talk very much. This is very interesting. One of the things that came to my mind fairly early on when you were introducing the model and the projections and so on is whether or not the models are explicitly distinguishing between multi-year and first-year ice as part of the process of doing these projections, and whether that distinction even really matters for this purpose. I'm thinking mainly the fact that multi-year and first-year ice have physically distinct properties that may bear on the rate at which they melt under different circumstances and so on.
Yeah. So I'd say we do simulate multi-year and first-year ice in terms of, the ice. Not all ice survives the melt season. So there will be first-year ice that grows in the fall, say. But some of the processes that influence how first-year ice and multi-year ice differ are not that well simulated. So, for example, snow on level ice versus ridged ice, we don't really account for. There's a lot of observational evidence that's coming out showing that snow is often blown from level ice onto ridged ice. That level ice is often more kind of first-year ice. We don't account for that in the climate model, say, and that could have implications for these ice melt processes in a warming climate. Melt pond coverage on first-year versus multi-year ice. We have some elements of that, but it's not terribly well constrained by observations or theory. So there's definitely more work to do in terms of improving those aspects of our sea ice models, I'd say. And I do expect that they would affect these feedbacks and affect, our projections of a changing climate.
Thank you.
Okay, looks like Till, you have your hand raised.
Yes. Can you hear me?
Yes,
yep.
Perfectly.
Hi, Marika. Thank you for a great talk. I had two questions, if I may. Just one quick one. Erika Rosenblum and Ian Eisenman showed that a lot of the models, because I was struck by how good your observational fit is to the large ensemble in the decline of the sea ice. And they showed that a lot of the models get the sea ice better now in the CMAP5 compared to the CMAP3 because, if I remember correctly, because basically they just ramped up the warming And so as a result, you don't quite get your sensitivity right. So I just was wondering what for your large ensemble, where you fall on the warming compared to the observed warming.
So this CESM1 Large Ensemble has a quite reasonable global average warming. I mean, I know the study you're talking about where they showed that models that have a better sea ice loss also have more global warming than observed.
Yes, right.
They compare quite well with their observed sea ice loss, but they do it because they have a global warming, which is larger than observed.
Yeah.
I think our global warming is quite reasonable in the CESM1, but we are on the, in terms of our sea ice loss, our ensemble mean is quite a bit higher than the observed ice loss, right? So, I mean, the loss in the observations is larger than the loss in our ensemble mean. And so I don't think that we necessarily contradict what was in the Rosenberg and Eisenman paper.
Did they consider the LE?
I expect that they considered our CESM1 simulations.
Right.
I don't know if they used the large ensemble, but we do have other CESM1 simulations that were submitted to CMIP 5 that were, kind of a smaller number of ensemble members. They used they used a different ozone forcing in the 20th century. So there are some modest differences, but I think for this question, it would be basically the same kind of results. So I think we probably fall within the scatter in their analysis, and we do have less ice than observed if you look at kind of ensemble mean metrics, even though we're within the distribution of ice loss pretty good across members. Yeah.
Can I bother for one second question? I was just wondering, when you have that 1980, so your predictability basically is 0 in 1980, and then suddenly it's in 1990 substantial, and it stays substantial. And I was just wondering whether that might be related to the other thing that you showed, that your forcing becomes detectable in 1995. Whether those are totally different.
I think that they're different because in this case, these are just 1-year predictions. And so I guess actually, I'm rethinking my answer to your question, so sorry. So I think you can see here that a lot of the reason why you get a predictable sea ice on these seasonal timescales in these warmer decades is not because the predictions have less variance across them than they did in 1980, but it's because the internal variability is growing. And that is a climate change signal, right? I mean, as you move into these warmer decades and the ice thins, the ice area becomes much more variable. And so that's a large reason why we have improved predictability. And so in this 1980 or 1990 climate state, I mean, you get this emergence of the anthropogenic signal in terms of the mean state. We haven't looked at the emergence of when that ice area variability increases, but that would be interesting to do, and they might go hand in hand. And if that's the case, then I'd say that this could be related to that sort of time of emergence that you see in the mean ice area. Because our initial conditions are much more important for constraining sea ice when it's just more highly variable. Does that make sense? Yeah. So it would be really interesting to look at a time of emergence for these variability metrics in addition to the mean change.
Right.
Yeah.
Great. Yeah. Thank you.
Okay, we have another question from Nu Chen. Nu, do you want to go ahead and ask your question?
Yes. So my question is just the perfect model you showed is starting in January, and I just wonder if we can like start that in summer, and what would that lead to? Would it lead to a higher unpredictability in model?
Yeah, so I do think, yep. These are all looking at January 1st predictions, predictions from January 1st. And we do see that there's sort of a predictability barrier in the sea ice on these seasonal timescales. So other people, Mitch Bushik has a paper on this. David Bonin has looked at this as well. So if you initialize your predictions kind of after this melt season has started, you have a much better chance of predicting what's going to happen at the end of summer. So there is very much an initialization month dependence on our predictability characteristics. And it's not just, that closer to what you're trying to predict, the prediction skill goes up. I mean, that's true, but it's not just a linear thing. Basically, if you start your initializations after ice melt processes have kicked in, you do a much better job of predicting the end of summer sea ice cover. So we're planning to look at that a bit more in the context of these perfect model experiments, these kind of perfect model framework. But it's, definitely some of the reason we don't have predictability in that 1980 climate state here is because we're initializing on January 1st. I expect if we initialized on June 1st, we might have predictability for the following summer, September. Yeah.
Thank you.
Yep.
Okay, and we have one last question, which is kind of related to a question that I was going to ask. I was kind of wondering myself if there are if you had other explanations for the cause of the increased interannual variability in terms of, are things in the atmosphere also, exerting stronger year to year, forcing variability. Well, maybe I shouldn't use the word forcing, but things like increased storminess or other things, or cloud cover. Could that be also enhancing the interannual variability in the modern climate? But Yinghui Liu also asks, whether increasing the spatial resolution of the model or increasing certain processes, i.e. clouds and other things, whether that could improve the ability to predict sea ice from year to year.
So I'll take both. I'll take the first question first. So I think that in terms of the increased variability in the sea ice that we see, I do expect that there are other things that likely play a role. We definitely see that the mean sea ice state is part of the story. And I think there's more work needed to look at, storms in the Arctic, other aspects that might also modify the variability of the sea ice, and how those are changing in the warming climate. So I think that's definitely a, active and interesting area of research to look at other aspects why the variability changes in the warming climate. In terms of model resolution and other aspects that might change our kind of seasonal predictability characteristics of sea ice, there are some indications that our climate models might be actually too predictable in terms of sea ice on these seasonal timescales. And so Ed Blanchard, Wrigglesworth, and Mitch Bushik have a paper that suggests that to the extent that you can, looking at the observed record. So actually, I think it's maybe more likely that with higher resolution atmosphere and better simulated cloud processes and things like that, we might actually add more noise to our system, more storms, more wind forcing of sea ice, say, that might actually decrease our predictability on seasonal timescales instead of increasing it, but would be more realistic. So I think those are also things that we need to consider. And there's processes in the sea ice too, wave sea ice interactions, other things that I think could actually cause a reduction in our prediction skill if we weren't working in this perfect model framework, but instead we're working in kind of predictions of the real world. So, but it's an interesting question, and I think it's definitely something that we need more work on.
Okay, well, thank you very much again for outstanding talk. I think, yeah, there's a lot of stimulation for future research activities. So I want like everybody to join me in thanking Marika for an excellent talk, and yeah, basically I wish everybody a great rest of your day.
Yeah, thanks a lot.